I blame it on me, like, sucking. So,
Are we going to get through all of calculus 2 before the end?
yes, with some examples left off. I always aim high, and then I don't always succeed at getting everything done I want to get done. So, I'll keep trying. Well, I'm an optimist. I'll keep trying. Okay. Have you guys, anybody watched the Avatar when you were kids?
Yes. Oh, yes.
I'm like Sokka, still got my positive attitude. Okay, so here's the thing. We're going to talk about what these Taylor series are used for. I know this chapter is kind of silly in this respect because unlike other stuff you see in calculus, it doesn't put the thing you're going to use for first, which makes you understand why the heck we're doing all this stuff in the first place, okay? So I will actually try to think about how to fix that for my future classes, and I'm sorry that doesn't fix the problem for you guys. But so if you have a function f of x that's equal to the sum of its Taylor series at a point x equals a, this means that this function has the following representation. The sum from n equals 0 to infinity. And then that's just saying the function is equal to the sum of its Taylor series, which is the nth derivative with a plugged in over n factorial times x minus a. To the n. Yes, I was just testing you there. So, and what this can do, what this is useful for, is this lets you estimate f of x near x equals a. It gets this, you get an approximation of your function. And using a partial sum. Do you guys remember what I mean by partial sum? The whole sum is you add up everything, right? Partial sum just means you... First couple terms. You stop at a specific point, be it 5, 10, 7, 1,000, whatever, okay? But often it can be quite less, quite low. So, this first question, Jill actually wrote down like the Taylor series formula, but these kinds of things are always kind of gross. So what I'm going to do instead is like just find the first few terms, and then we'll just kind of expect that we could find the rest if we had to, okay? So to find the Taylor series of f of x equals root x centered at 1, the first thing you do is you compute a whole bunch of derivatives. Does that make sense? And then what number are we going to plug into these derivatives? We're going to plug in 1, okay? If it was Maclaurin series, what number do you plug in? 0. Okay, great. So f of x is root x. The first derivative is a half x to the negative half, right?
For future reference, what is 0 factorial?
1.
Okay.
I definitely did say that, but yeah, 0 factorial is defined to be 1. I've said that more than once, I think, right? Okay, but you know, you can't remember everything I say, even though I know you hang on my every word.
Always.
Laugh at my funny jokes. Come on, give me something. I need to pick me up today. What's the derivative of 1/2 x to the negative 1/2? X to the... Yep, let's do 2 more. Third derivative is positive or negative?
Positive.
And it's 3/8 x to the negative 5/2. And then, did I say one more? Fourth derivative will be negative 15/16 x to the negative 7/2. Thank you. Okay.
That multiplier, it looks like it's kind of trying to get bigger again.
Yeah, so let's write about this. So the function f of x, if it's equal to its Taylor series, is equal to the function evaluated at 1, right? Plus the function derivative evaluated at 1, technically over 1 factorial, times what? Is it just x, or is it x minus 1? Plus second derivative at 1 over what factorial? 2 times x minus 1 to the second, plus third derivative at 1 over x minus 1 to the third, and then, you know, plus, like, if I just say dot, 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 you know, that pattern continues, right? That's just that infinite sum with stuff listed out as opposed to written in summation notation. Does that make sense? Okay.
Wait, why are you putting the x equal to 1 and then the a equal to 1 separately?
I'm not putting the x equal to 1 and not the a equal to 1. I think that you just have confused as to what order stuff is in. It was x minus a, always. So that's why the number after the x is the a.
Okay, so you're substituting 1 for x in the original equation?
Yeah, but this formula, look at the thing above, look at the box.
Yeah.
Look at how it says f nth derivative at a. Oh, I see what your problem is, the notation. This should have said a equals 1.
Okay.
Okay, that really is the way it should be given.
Got it.
But, it could be phrased as, this is my center value as well. So, okay, I understand now. All right, now plug in those numbers and just give me kind of a list. So f of 1 is 1, plus then we have a half times x minus 1, right? Yeah.
So why is it, for the first derivative x minus 1 and the second one is times x minus 1 squared? Why isn't it just x and x squared?
So, yeah.
Because if you look at the thing above, okay, look at the box above, it's always x minus a to the nth power. So if you're on your first term, it's x minus a. Or if your 0th term is x minus a to the 0, which is nothing, right? You see how that always is to the n. So the numberth derivative matches the power on that thing. And it doesn't change. If it's x minus 1, it's x minus 1 for all of them. Much like if it's a Maclaurin series, it's x for all of them. Okay, then next we're going to have, is it positive or negative?
Looks negative.
It's going to be negative, so just actually get that correct, which my eraser function ain't going to work, so grr. Let's put the whiteout function instead. Minus 1 over 2 factorial times a quarter, x minus 1 squared, and then just the last couple, plus 1 over 3 factorial, 3/8, x minus 1 to the third, and then what would come next? 1 over 4 factorial, right? Times 15/16, x minus 1 to the fourth. And there'd be many more terms. Putting that into summation notation is gross and tricky, and I'm not gonna bother because this is not the most important thing on today's lesson, okay? But do you get the idea as to how you sort of can list this out and then plug numbers in and find the polynomial? As in, I know that there's more stuff that comes, right? But do you understand how you find the first term? How you find the second term? Does that part make sense? Okay. Do you understand why this is 1 over 3 factorial? Does that make sense? Okay. So what we're going to do in today's lesson is we're going to use a truncated sum to estimate the infinite sum. And we'll talk about how accurate those estimates are. So those are called Taylor polynomials. So this next question says to find T0, T1, T2, T3. The numbers on these refer to what n you go up to. So T0 is just the first term. So in general, T0 of x would just be equal to that f of a thing that you have. And those are called Taylor polynomials, and they're polynomials because they're finite and they've got x's to powers, and as opposed to an infinite sum, which is not a polynomial. So in this case, that means that we have that sum we wrote on the last slide, which was f of x is equal to, what was it, 1, right? Minus or plus? Must be minus next, right? Plus, okay, so it's plus a half times x minus 1, right? And then next came 1 over 2 factorial, right? Times a quarter, x minus 1 squared, right? Okay. So T0 means you just take this term only. That's it. So T0 is just 1.
That seems like that'll always be inaccurate.
And of course, it will always be really inaccurate, right? You're estimating and what you're kind of saying is you're saying, well, square root of x is about equal to 1, and technically this is saying near a equals 1. But of course, yeah, estimating a root by a constant is a horribly inaccurate method, right? How do you make your method better? You add more stuff, right? Does that idea make sense? So what is T, if you have T0, it means just the first term. What do you think T1 means?
First term plus the second term?
The first term plus the second term. So we have 1 plus a half times x minus 1, which simplifies to 1/2 x plus a half, I believe, right?
Plus one?
No, it's definitely plus a half, because when you distribute this 1/2
Oh,
x,
yeah, I see.
you buy it? So, did you ever in your past lives approximate functions by lines?
Yes.
That is a line.
That is a line. Back in Calculus 1, do you remember there was a section called linearization of functions? Maybe you saw it, maybe you didn't.
It was pretty accurate.
It's like, it's saying, like, this is saying, like, root x, as in this picture, is about equal to this line. That line is the tangent line. It matches the function at the point and the derivative at the point. What's the second Taylor polynomial going to be? Not simplified, just tell me which things. Be the first 3, yep. So it'd be 1 plus a half times x minus 1. This will be minus an eighth times x minus 1 squared. Gesundheit.
That in your 2 factorial.
I multiplied 2 factorial, which is 2, by the 4.
Oh.
Which gave me 8.
I thought 2 factorial was a bigger number. My bad.
Does that make sense? How I got 8? But kicker was the first 3 terms. And now if you do some algebra and simplify this, what you end up with is negative an eighth times positive x squared minus 6x minus 3. That is a polynomial, right? Yes? And how do you think the polynomial approximation is going to compare to the linear approximation?
More accurately.
It's going to be more accurate, like for, like, say, more values, a wider interval of stuff. And there's just one more. What's the third one going, that was T3, what's T, that's all we're supposed to find. Okay. So those things we found, these are called Taylor polynomials.
Wait, was that T3?
I'm so sorry, that was T2 when I was trying again to test you guys. Apparently, not sleeping is not a good idea. That is T2, thank you.
Did the election keep you up too?
Everything well, yeah, I'm just a worry wart. T3. Of course the election kept me awake. It's just what it does. I'm old and I worry about things. So, T3 will add those first 3 terms plus one more, right? So we'll have the 1 plus the half x minus 1 minus an eighth x minus 1 squared. And could you remind me what the next term was? Just forgot. It's going to be plus.
1 over 3 factorial times 3/8.
Thank you. Times x minus 1 to the third. Do you see a pattern with the degree of your polynomials and the number of Taylor polynomial we got? That as in, like, the second Taylor polynomial has a highest power of 2, right? The first degree has a highest power of 1, right? And the 0th one has the highest power of nothing, right? It's got x to the nothing, so its degree is nothing, 0. And this guy, after you simplify it, it's going to work out to be 1 over 48 x cubed minus 9x squared plus 39x plus 17.
That's just the biggest term though, right?
Say that again?
That's just the biggest terms, not including the other.
Yeah, well, the degree of a polynomial is the power of its highest, it's the highest power of all of them. Yes?
So is this one where we would be able to make a infinite series out of that? Looks like a really complicated pattern.
Yes, this is one for which you can make, like, you were saying, like, how could I write this in infinite summation notation? Jill did that on the notes, and you're welcome to look it up. It's one of the ones where, like, as in, like, they're on Blackboard, and you can look at them there. And there is a pattern, but it's one of these ugly ones where you can't include the first few terms with it, and you've got to start your term at, like, n equals 2. It's, like, one of those disgusting ones, which we're not going to ask you that in a test, so I just don't care enough to, like, go through it in class. Okay? Does that make sense? Because it is just tricky, and it involves a pattern that's kind of factorial-like, but not factorial exactly, because it skips things. As in, it goes like 3, 5, as opposed to 1, 2, 3, 4, 5. So just not going to worry about it.
Yeah, if you gave me those 3 functions, I would not be able to figure out the 4th one.
No, exactly. It's tricky, and I suspect that also this 1/48 affects the pattern, and to really see if you keep it there. So don't worry about it. The point is that you can estimate a function. You had back in Calculus 1, you had estimation using a tangent line, and you can do better using a quadratic. even better using a cubic, and if you want to go even better, you can use powers of like 4, right, or 5. Back when I was in college, and I was your age, or approximately some of your ages, I definitely did this for like a wind turbine project we're looking at. My school was really windy, and we had to like fit a curve to a power output thing, and we used a Taylor polynomial. So here is a picture that's going to show you graphically how these things compare to the root function. You probably can't draw this, but it is online, so you're welcome to look at it. But you can kind of sketch what's going on in your paper if you want to. So here is the root x function. So we approximated this function near x equals 1. So that's our a equals 1, that's our center point. Okay, we're going to skip t0 because t0 is silly. Here is the tangent line, the t1. So there's t1 of x. Do you see how the tangent line appears to be reasonably close to the root function near x equals 1? So it's a reasonably good estimate near x equals 1. In green, which I'll just draw over, here is the polynomial. Do you see how that's sort of closer to the actual shape of the curve? And also closer for probably more values, as in your interval of accuracy probably is wider. Does that make sense? If you say I want this much accuracy, I probably can encompass more values. And the last one, the cubic, it's not completely obvious, but it actually, generally speaking, does even better.
No, that's a really wide interval of accuracy.
It's a reasonably wide interval of accuracy, yes.
So you can basically do this at any center point.
Yeah, so if you cared about like square root of 1.1, you'd pick your estimate to be near a equals 1, right? But if you cared about like square root of 1,207.6, maybe you would center it someplace different, right? Because the further away you get from 1, the less accurate all these things are, right? Does that idea make sense?
Is that how you calculate your graphs?
This is probably how your calculator approximates certain things. Okay, you can look in the you could probably just Google it, but I'm pretty sure when I Googled it for like how does my TI-89 do e to the something, it says it uses the Taylor polynomial centered at a value.
Okay.
So yeah, it does how your calculators work, I suspect,
Right.
okay, at least for some of them.
I don't know, if you did like t base of million or something, could you figure out the square root of 1,007.6?
You would need a value for which you could find the square root easily that was kind of close by.
Within 1,000?
Oh, like probably would be closer than 1,000, but something, there must exist something that's better than that. And then you would find the approximation somewhere near that. You did something that's in Calculus 1 where you were asked to like estimate this using a linear approximation. You had to pick the function and pick the points you were close to. That happened. It's section 3-10 in your textbook, like I even know where it goes. But, okay. Last question was, have you encountered that first thing already? And the answer is, yes, you have. It was in Calculus 1. It's called the linear approximation. If you want to look a little bit, it wouldn't take you long. It's section 310 in your textbook. That's where it is. Just kind of take a glance at that. Its idea is use a tangent line to approximate a function.
Does the secant line do better or worse?
The secant line is worse because the secant line goes through the endpoints and doesn't match at the point of tangency.
Got it.
Okay, so given your graphs, which do you think is a better approximation of square root of 1.1? So if you're asked to estimate square root of 1.1, which is more accurate? T1 of 1.1 or T2 of 1.1? Which one do you think?
T2.
Probably T2, because this curve, this one, as the curve, which is a polynomial, as in a quadratic, right? Is closer to root x at x equals 1.1 than T1 of x is.
So all of the t polynomials will be accurate at square root of 1.
Yes, they will all match at square root of 1.
They'll all perfectly matching square root of 1, but the higher you go, the closer you get out.
Yeah, the higher you go, the more accuracy you have, like further away from that number. Yeah.
So is A supposed to be that?
No, the A is still 1. 1.1 is a nearby value you're thinking about estimating. So the 1.1 really is like an x.
Is it possible to take the limit as that base number goes to infinity to figure out what the value actually is?
Yes, that kind of would be how you'd estimate. We'll learn an estimation technique to look at the remainders, which will allow you to like estimate that to a certain degree of accuracy. And this is a more general remainder technique than the AST or the integral test, because those only apply to integrals tests or alternating series, whereas this applies to everything. Okay, so what do these things mean geometrically? Do you have a question or do you know?
Yeah, I was gonna say they're probably talking about the absolute value of the errors at those values.
Yeah, do you guys get that the first one, so this one, this is, it's the error, as in how much you're off, i.e. you take the actual value minus the approximation. And you absolute value it so that you ignore the fact if you have an under or over estimate, you just look at the sign. Does that make sense? Now, the other thing that this tells you, this is the distance from the curve, or the point on the curve, to your estimate. Does that make sense? Like you have this curve, y equals root x, right? You have this 0.1 and you got some polynomial, right? Some sort of quadratic thing. So like if this is 3 out here, this is t2 of 3. This value is root 3, and that absolute value is how far apart they are, right? And when you absolute value it, you just get rid of the sign. You lose the information if it was an under and over estimate. Okay. And then this next question, which of these quantities do you expect to be larger and why? Because they are, I think they are the error, right? So when are you going to, we centered our thing at a equals 1, right? So, or thinking about that picture, is the distance from the 1.1 rooted on the curve to its polynomial going to be bigger or smaller than the distance from root 3 to 3? Yeah, the second will be larger.
And these are still centered at.
Yes, yep, we're still talking about being centered at 1.
Because basically we calibrated our whole process for 1.
We calibrated our whole process for 1. That kind of is a good way to think about it, yep. The second will be larger as t2 of x is, we'll say, farther from root x, the farther we are from our center value of a equals 1. So if you wanted to use if you wanted to use a polynomial to estimate like root of 3, you might need a lot more terms to get the accuracy to extend that far. Does that idea make sense? You need to add in more pieces, like go to like T100 or something like that. Or you also could pick a center value and you could pick 4 instead, which is closer, right?
I think you might get wider accuracy at 4 as well, because it has some pretty unique properties.
Possibly. I think it does have something to do with what your derivatives like sign is, as in how steep it is. So it's possible. Okay, so suppose you want to approximate f of x equals e to the x. Find the Taylor polynomials of e to the x and use them to estimate at x equals 0.2 and 3.0. So one thing that was not stated here is where to center your value, right? No one said. Do you agree? Okay, so I think what we should do, let's just assume that what's meant here, and I know that my notes did this, we're going to assume we're centered at 0. Which means we're actually looking at the Maclaurin series, right? And you can use stuff that you know. For e to the x, that's equal to a sum from n equals 0 to infinity. So one of the ones you actually have to memorize. What is it? Great. X to the n over n factorial. And then just list out what the first few things are for me. Which is just x, right? Plus. Yep. Plus. Exactly. There you go. And that keeps going. So can you tell me what T2 of x is going to be? We notice the pattern with the degrees, right? So it's the first how many terms? The first 3. So this will be 1 plus x squared over 2 because 2 factorial is 2, right? Okay. Now, e of 0.2, now 0.2 is pretty close to 0, right? Is going to be about equal to T2 of 0.2, as in plugging 0.2 into that polynomial. Does that idea make sense? So this would be 1 plus 0.2 plus 0.2 squared over 2, which comes out to be 1.22. So just 3 terms. This 1.22 isn't that far from the value a calculator would give you of 1.221 and stuff, right? Okay, what do you think is going to happen when I try to estimate e to the third? It's going to be a lot worse. So then what are you plugging into your polynomial? 3. And that would be 1 plus 3 squared over 2, which comes out to be 8.5. Which is a horrible estimate, right? Because the actual value the calculator gives you is 20 point stuff, right? So, okay.
Talk about horrible estimates and getting flashbacks of last night.
All right, what's T8 of x going to be? A lot more stuff. 1 plus x squared over 2 factorial plus x cubed over 3 factorial up to blah, 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 blah. What's the last thing going to be? X to the 8th over 8 factorial. And if you had infinite patience, I believe you can plug the numbers you need to into this function and you'll get this answer. If you want to estimate e to the 0.2, that'd be about equal to plugging 0.2 into this polynomial, which is kind of amazing. You get 1.221403. Okay, so you get just going with 8 terms, already estimating e to the 0.2 is the same thing your calculator gives you. That's the accuracy you have. And e to the third gets a lot better as well. That's about equal to plugging in 3, and that comes out to be 20.009152. So that's not
like perfect accuracy, but it's way that closer.
Yeah, so it started out pretty good, and then it got like only, and 8 terms is not that much for, like, say, a computer to handle, right? Does that idea make sense? As in, you by hand, pain in the butt, right? But if you could program a computer to, like, keep adding in terms when you wanted more accuracy, I think that's what your calculator does. It probably, like, computes these things until it gets enough decimals matching that it's like, okay, this is good enough. I suspect. So that's one thing that series are used for. You use truncated series to estimate functions. It is quiz time, so I do recognize that.